Welcome everyone to today's webinar, 80 megapixel Trimble aerial camera, reaching new heights. My name is Gregor Wilhaug. I'm a product line manager with the Trimble Geospatial division. With me today is Tobias Tölk, our EMEA sales manager for the Trimble aerial camera. Tobias has a background in surveying and is with Geospatial division for over 10 years. So before I hand over to Tobias, I would like to give you a brief overview of the Geospatial division and our product portfolio. So in this slide you can see that within the Geospatial division we cover the entire geospatial workflow from data collection over data processing to information extraction for the land, aerial, and even the satellite workflow. So on the land side we have mobile data capture systems, hardware systems. On the aerial side we have aerial cameras and digital sensor systems. On the software side, we offer a suite of data analysis and processing for mobile feature or mobile data collection and feature analysis. On the airborne and satellite side, we have two software suites, Info for photogrammetry and point cloud processing, and the Cognition package on geospatial data fusion and object-based image analysis. So our mission really is here to transform geospatial data into geospatial intelligence. With that, I would like to hand over to Tobias to guide us throughout today's webinar.
Yes, welcome everybody to the webinar about our new 80 megapixel camera. I'd like to give you a short overview about the points I'm talking today. I will start a little bit about the camera itself with 80 megapixel. I will talk shortly about an upgrade option for existing Trimble aerial camera owners. I will have a short comparison to large format analog cameras, which may be very interesting to see it from a different point of view. I will talk about our forward motion compensation technology, which we introduced at Intergeo last year, and it's now also available for the 80 megapixel camera. And I'm here, and I hope that a lot of you have some questions which I can answer and give you something I may miss in my presentation. First of all, the 80 megapixel camera is having a sensor where we have a 5.2 micron pixel size. I will talk about the number of pixels in the next slides. We added the forward motion compensation in this camera as well, and it's a pure mechanical forward motion compensation where we really move the sensor during exposure, like you know it from the old analog cameras where you have the under pressure plate where it sucks the film to and then you move it forward during the exposure. The weight of the camera is approximately 2.5 kilograms without lens, and the lens weight can be between 500 grams to 1 kilogram depending on what kind of lens is used. So you see the camera is extremely light-weighted, and this makes it very usable in ultralight planes or echo planes or small planes. Even some UAVs which have a certain payload can carry this camera. Lens options are 35 to 100 millimeter, and we have some special lenses with 150 and 210 millimeter available for very special applications. Also, the dimensions of the camera are very small. You see it's very small and very compact, so it easily can be put in planes. And we have an electronic leaf shutter, which has a 1/1000 second exposure time, and we increased the shutter lifetime in the last months again by adding some new components. Here are some images which I like to show you from small aircraft where we put the cameras in. One on the right side is the trunk door of a Cessna 172, where one of our customers made an experimental license for a shifter where a gyro mount is on, and he can shift it in and out during the flight. So during start and landing, which is a critical phase of each plane operation, the camera is inside the plane, and once he's on the mission altitude, he presses a button and shifts it out. Again, this is not a commercial thing, it's an experimental license, but it shows you what is possible with this camera. The other image shows you a pilot training school in China where military pilots are trained and they use this dragon wings, and we even had this camera once underneath the dragon wing where you can see that the light and small camera is very capable for things like that. Getting over to the lenses we are offering, and here we have also the number of pixels of the new sensor, which is called the IQ180. It's 10,000 by 7,000 pixels, which is 5.2 micron. We made a small calculation that we say we want to have a ground sample distance of 10 centimeter, and so we get a footprint of nearly 1 kilometer by 800 meter approximately. What I like to point out here is when you look at the different focal lengths, where we start with 35 millimeter going to 100, that you can get this 10 centimeter GSD from different altitudes. Where is this good for? It's, for example, very good if you have bad weather conditions and you need data quickly. For example, in rapid response activities after a thunderstorm, a hurricane, a tsunami, or an earthquake, and the weather is not good, you can fly underneath the clouds and get image data. This image is maybe not as perfect as under sunshine, but they are pretty good to get the information you're looking for. The other side of this table shows you the 100 millimeter lens, where we fly in 1.5 kilometer and still get the 10 centimeter GSD. So this could be used when we fly around airports, where we have to stay in a certain altitude not to interfere with the incoming traffic. This shows you that we are very flexible and that you can adjust the focal length due to your mission you want to do. Let's go shortly in this analog replacement with 80 megapixel, what we are talking about at the moment sometimes with customers. I want to go back to those times when we had this 9x9 inch analog film material, which is still in use in several parts of the world, and it's still something which it's very good, and you can get a lot of data out of it. But if you scan it with a 20 micron, it's approximately 10 by 10K pixel from the image size. Now the new 80 megapixel camera has this format from the sensor, which is 10 by 8K pixel. So in one direction, which is the long side of the rectangle sensor, you have the 10K. And this means that you get nearly the same information or the same resolution as from a large analog image. And on the other side, which is 8K and keeps this a long track, then you may have to add some images on your track, but it's digital images, so they don't cost you film material or development and scanning, so it's an easy calculation. And you see that you have now the potential with a very small and light camera to get the same resolution as from an analog camera with 9x9 inch negative format scanned with 20 micron. And this makes this camera really a thing where you can think about replacement for the old analog ones. Coming over to the forward motion compensation, we have in our office for calibration reasons a spinning wheel, and we made the Trimble logo on it. And then we spin it with some parameters which you can see down here. We had a 72 millimeter focal length. We use an extreme long exposure time of 60 of a second, which you would not use during a flight, but for calibration reasons it's quite good. Then we spin it with a certain speed, which is the same as 50 meters per second, flying 500 meters above ground, which gives you a ground sample distance of 4.1 centimeter. And you can see that we move the sensor during this time for 18 pixels, and we keep an aperture of 8. And when you look at both images, you see on the left side where we use the FMC, it's very bright and crispy and clear, and you get all the information in the image. And on the right side, you definitely see that this image is blurry and you cannot really use it in later post-processing. So there you see what the difference looks like, and I think it's very good to see it one time really in nature, even if it's a spinning wheel. Now here's an image from a flight we have done with this forward motion compensation, and now you see that we used a 125th of a second exposure time, which is also a long exposure time, and we had an 8 centimeter GSD, 1,000 meters above ground, and 110 knots. It's not so fast, but it's a good number for a Cessna 172 to fly in a mission. When you look at the lines of the sporting ground, and this is something I like to point out, they are all crispy and clear in all directions. Some people may come and say, oh, look, if it's in flight directions, they will look bright in any way, but also the cross-track lines of the sporting ground are very clear, and you can see them, and you see there's no smear or any blur in that, which is, from our point of view, a very good proof that it's really working. Here now is an image from the new 80 megapixel sensor camera with forward motion compensation on. And you see the complete image in the corner, and there you see what kind of ground we can cover with one image, and we have here a 6 centimeter ground sample distance. And the big image in the center where we zoomed in, this is a 1:1 resolution, and here you see that even the cars which are moving in the roundabout are very clear, and you don't see any smear effects. We were a little bit lucky, or I chose this image because of this plane down there, where I think also planes are very important in our business, and it's a nice picture. We had another one which I thought I could put in, where you see a convertible car driving there, and you can really see that two persons are sitting in. So maybe on the next presentation I have this in there. Okay, I have a small summary about this kind of sensors and kind of cameras. What we see at the moment is that the sensor development is very fast. Every 2 years we see a new sensor coming to the market. We started many years ago with the 16 megapixel over the 22, the 39, the 60, now to the 80. And every 2 years normally there's a new sensor available. And this shows you what kind of dimension is in this market and in this development of sensors. Especially this is driven by the professional photographers which want to have a higher resolution and a higher resolution. And that you get an understanding, I'd like to tell you that approximately 7,000 sensors are sold in the professional photographers market, and a smaller number is sold in the aerial market where we are working in. Another thing, this sensor was announced first time at the Photokina in Cologne last year by the company Phase One and by the company Leaf. And they start selling it in early this year around April, and we got the first one in May in our hands. And we start working to put it on our cameras, and I think we did a very good job to have it ready in 2 months. And this shows you that we really are in this business and that we can provide our customer in a very quick time after release of a new sensor with the sensor for their production or for their usage. Again, this camera was announced last time and introduced 2 weeks ago at the Photogrammetric Week in Stuttgart, which was a very nice show, and we had a lot of customers coming over to take hands on the camera. The modular design and the easy upgrade, which were already implemented to all these cameras in the past, is still part of our camera today, and we offer to upgrade to our customers the sensor. So you don't have to go and buy a new bag. You can use your existing bag, your existing camera, your lenses, your electronics, your cables, and you can ship the camera to us, and we only replace a digital bag, and you have the latest sensor technology in there. The camera is available as standalone or as part of the systems, and I will spend some slides in the end of my presentation to talk about the systems as well. As I said before, existing cameras can be upgraded. We need the camera in our office to do that, to do calibration, maintenance of the camera, and to upgrade it. And we can take off the bag you're using or the sensor you're using at the moment, and then we can put the 80 megapixel on. And this really improves your image resolution with the latest sensor technology. So you can be more competitive, and you can save a lot of money by reducing the flight lines you fly, because keep in mind, if it's cross-track with 10K pixel, you really can get rid of some flight lines. And all of you, I think, know that operation in the air is one of the biggest cost-spending factor in your business. So if you can reduce this by flying less lines, it really gives you a very good competitive situation to your competitors, which may not have this technology installed yet. Shortly back to our geospatial division and what we're doing there. And there we are thinking all the time how we can get our products closer together, how we can offer you the best out of Trimble, and what is our core technology, and what is our business, and what's our knowledge in there. When we look shortly at this slide, you see that there's down 2 cameras. One is the one we are talking about it. The other one is another camera which is in our portfolio, which is a very special design, mostly for military applications and reconnaissance, because there's an extreme fast shutter in there and we can work with extreme long focal lengths. But when you look on the yellow side of the slide, you see there's an upgrade path, that if you say, I may start only with the camera in the beginning for my business, and then I make some money out of it, I will generate revenue because I'm doing small projects, and after a while you want to move in the business of doing corridor projects or doing other projects, you may think about adding an IMU GPS system to it, that you get direct georeferencing, that you get inertial data for your camera pictures, or your images, sorry. And besides, you may add a flight management system. This is what we have under the Trimble DSS. The Trimble DSS is a digital sensor system, so it's not a camera in this way. It's really an IMU GPS, a flight management system, and post-processing software together, that you can very quickly get autophoto production established with this system. And then you see small errors to the software side, and also there's an upgrade path available from Trimble, where we have the info suite, covering mainly everything about autophoto production, mosaicing, digital triangulation, mapping purposes, and anything what you can do with aerial images. Maybe aerial images and pure photogrammetry is not the only thing you like to do, so you can think about being a LiDAR company as well, and then you can give us back the DSS and we can modify it into the Trimble Harrier, which you see on the right side, which is a full turnkey LiDAR system. So you have all the functionalities of the DSS plus a laser plus a full LiDAR system, including post-processing software. And also there we have on the info side very nice models in our software which can be used for surface modeling, digital terrain modeling, and a lot of other applications which fits together. On top of it, we have the eCognition software, which is for extract features, create geo information, and this is if you want to do more, take more information out of your images as only the pure autophoto or the map or whatever you're doing. So it's very helpful. I'd like to point out at this moment that we have tomorrow a very good webinar, which is done by my colleague Thomas Koch. He will talk about especially info software and eCognition software, so you are all invited to join in there, and we think there's a lot of interesting things you can learn. Now let's start over a little bit where we talked about where is the camera inside, or where is this image sensor inside, and as I said before, one of the parts is the DSS. Here's the DSS in a special version for RapidOrtho. It is not that the hardware is extremely changing in RapidOrtho, it's more a software issue, so there's a special software with it, and this allows you to generate very quickly mapping-grade autophotos or stereo products. It's fast and efficient for mapping purposes. The very interesting thing is that due to this software product behind, we are able to get a 1-to-1 ratio between flight time and post-mission processing for autophotos. This autophotos may not have the highest accuracy, but again, it's rapid autophoto, so it's more for disaster management or military information where you need information very quickly. I sometimes say it's very important because think about you have a flooding, like the horrible flooding you have seen in Australia last year, and then you have people sitting on the roof of their houses waiting for the rescue team. And if you have to check where are people sitting on the roofs of their houses, you don't need accuracy of 1 centimeter. If you drive with a boat by these houses, people will scream and shout, and this means if you have the accuracy of 1 or 2 meter, you're much good, or you're very good in space to go there and rescue these people. And this is possible with 1-to-1, so this means 1 hour of flight operation capturing images would be 1 hour of generating a complete autophoto. And this is really a quick way to get data. The next thing is the Trimble Harrier, where the camera again is inside or the image sensor is inside, and here we have a complete ruggedized system where you have a sensor rack. Inside the sensor rack is the laser, the LiDAR itself. Then you have the IMU on top with some electronics, and you have space in the front part of it for 1 or 2 cameras. This could be an IR and an RGB, or an RGB only, or even a thermal camera, or whatever is needed for your missions. We have a computer rack to store all data, and there we have, for example, a power supply unit in there, which gives you enough power if the power in the plane breaks down to operate the complete system for 2 to 3 minutes longer, to either get the power back online or to go and drive down the system carefully that you don't lose any data. The other possibility is that this power of the battery is enough for 30 minutes data collection for GPS. So if your post-processing is beyond the PPP version, then you can use it after landing the plane to switch off the engines, and you let the battery run the GPS collection for 30 minutes, which is very nice and convenient, and pilots don't have to sit 30 minutes in a plane with running engines. They don't like that so much. The operator display shows you all what is needed to get the information about the flight, about the status of the laser, of the camera. You get an overview with the histogram function. You get a waterfall diagram of the laser. And the operator gets really all information about the system. The pilot display shows only the track to fly on, because the pilot is not interested in the laser or in the camera. He's interested to fly on the line. So he sees only this information, and the operator can also say that the pilot should see something different. It's a complete turnkey solution. And when you look at this slide, you see that there is a system architecture I have explained to you shortly before. And also, because it's a turnkey system, there's a software package coming together with it. And the software package allows you to use all the data from the Harrier to do your point cloud calculation, classification, DSM, DTM generation. You have a coverage control, you have a quality control, and you have, of course, a software which is needed to work with your IMU and GPS data. If you run a camera with it, you can produce autophotos or true autophotos directly from it. And also the software has some special products we added to this, which is for counterline survey or for mass calculation, which is a big deal when you think about open mining and you fly about open mining and you need all the counterlines or the mass calculation from that. So it's all embedded in the software and it comes together, so it's really a turnkey system. At the end of my presentation, I want to talk very shortly about one of our biggest advantages at Trimble, that is that we are very, very good in customization. Here you see a Harrier again, and you will recognize a computer rack and the monitor for the operator and for the pilot. But when you look at the sensor head on the right side of the picture, you see it looks completely different. It looks different because the customer came over to us and he's flying a Robinson R-22, which is a very small helicopter. And he came over and he already had this pod which you see there underneath, and you want to have the sensor inside, and the standard one would not fit in there. So we have to customize it. For this we have a clever team of engineers and labels which can do that. We have workshops with machineries for that. So what we did is we changed it, we customized it. And other companies sometimes came over and say, look, this is a product, here it is, buy it or leave it. So you can come over and say, look, I like your product, but I have this strange aircraft. However, it looks like, can you help me? And then we have the team to look at your aircraft, get some measurements, some sizes from your aircraft, and then we can see how we can fit it in. And this is what we are really strong in. And I think this is an advantage for our customers, that we can take existing technology which is inside our company and inside our division and then customize it in this way that it fits to your needs. This brings me to the end of my presentation. I hope you liked it. I try to keep it very short, that we have now some time for questions and answers. And I welcome you to ask your questions. Again, you see there in the question and answer button, you can type them in and my colleagues will then read them and let me know what we are talking. And I hopefully can answer them.
Thanks a lot, Tobias. And the questions are already coming in, so I will try to get them sorted out as we speak. One question was whether some of those questions might have been answered over time already, since they came in during the talk. But one question that came in was whether the camera does have an option to use a GPS and IMU.
The camera itself, it's a camera itself. So what we have, the DSS is coming together with IMU and GPS. If you have already an IMU and GPS system in your company, the camera has all the connectors you need to connect it to it. So we send out an event signal, for example, if the shutter is at 80% open and the integration time of the bag starts, it's a TTL level open collector. We have the connection for triggering the camera from an external flight management system, and also there's only a shortcut, means pulling down to zero or to ground, and it's very easy to connect. So it's mostly two cables which have to connect to existing systems, or if you're looking for a complete solution, it would be the DSS in this case.
Another question that came in was what the number of output bands for the camera is.
3, it's an RGB. And the color depth is 16-bit.
One question was whether all Harrier systems actually come with a laser, or whether come with a camera, and whether a Harrier system also can be purchased without a camera coming with the system.
The camera is an option for the Harrier. Normally, I would say that 90% of the Harriers are sold with a camera, but it's an option. So if you say, I don't need a camera because, especially let's say open mining, if your job is only flying open mining where you look all the time at brown earth, a camera may be not needed and you get your mass calculation out of the laser data. So in this case, you don't need a camera and you can buy the Harrier without a camera, but the camera is an option and could be 1 or 2 cameras which fits in.
Okay, brilliant. Thank you. One question was, on the radiometric as well as spectral resolution of the camera, whether you could go into a bit of detail in this side.
So it's the camera is only capturing visible light. This means the camera is sensitive up to 720 nanometer. So you get the red channel, the green channel, and the blue channel. Obviously, the sensor itself would be also able to capture the near-infrared up to 1200 nanometer, but due to the Bayer pattern, the DALSA sensors which are inside have inside the green pixels an IR cut filter. So it's not only a green filter for the green pixels, also an IR cut filter, which makes this sensor with the RGB sensor with the Bayer pattern, not very perfectly for near-infrared. If near-infrared is needed, then we have to go and use a dual camera system where we have one RGB sensor, where we have the IR cut filter cutting at 720 nanometer in front of the sensor, and we have a second camera where we use the DALSA black and white sensor. This DALSA black and white sensor is not yet available with 80 megapixels, but with I think with 60 and 39 megapixels, and they are black and white only. So they can capture the IR, and then we have an IR open filter at 720 nanometer, and the footprint of both sensors is identical because the physical size is identical, only the pixel number gets smaller. This means that your RGB resolution would be a little bit higher and your IR resolution would be a little bit lower. But later in post-processing, when you make the decision that the autophoto output should be, for example, 10 centimeter or 20 centimeter, you can adjust it that it both fits together. I sometimes call it a kind of punch sharpening, which is not 100% right from the technology term, but maybe to understand that it works well. And then you can put two cameras in there, and we can synchronize the cameras that they're really exposure at the same time, and the synchronization accuracy is better than 200 not milli microseconds, and in 200 microseconds your plane moves nearly nothing.
I got one more question coming in, quite interesting. The question is, what are our experiences, or if we could go into some more detail on the tag in UAV systems?
Oh, we have not so much direct experience in this way that we have them really in operation. But we have done a lot of tests, especially with companies building up UAVs for the defense industry, and we have done a lot of test flights with them, and all the tests shows very good results. But keep in mind that most UAVs which are used in the defense industry have payloads of 5 kilogram or 10 kilogram, even up to 1,000 kilograms. They're big, very big ones. So then it's more like a standard plane. Experience with this UAVs, which are in the understanding today when people talk about this UAV business, which have payloads of 500 gram, we cannot provide the camera to because the camera is too heavy. And this UAVs which have a payload of 3 kilogram, we have done some tests already which are very, very promising, but we didn't follow up so much because we are providing in this case a camera to our customers which are implementing them by themselves in UAVs. There was a very nice project, I think 3 years ago, from a university here in Germany. They purchased the camera from us and put it in a UAV, and it was a fixed-wing UAV, not the typical helicopter stuff, and the camera was exactly on the payload level, but they did a very good job with it. So if somebody's really interested in this, please visit the Intergeo or send me an email, because it will take me longer than I have at the moment to go in details in that.
Oh, okay. One more question came in. The question was whether the aperture and focus can be mechanically changed during the flight. Mechanically changed is, I see this question on my monitor as well. Mechanical changed is nice. It's electronically controlled, so yes, it is. It's a mechanical aperture and it's a mechanical shutter, and you can, during the flight, from the operation computer, means from the monitor or the touchscreen monitor the operator is looking at, you can change either the exposure speed as well as the aperture. Besides, we have normally a light meter connected to this camera, then we can put it on aperture automatic. This means that you fix the exposure time to keep this stable, and depending on the readout of the light meter, the aperture is open or closed, that you maintain the same quality of the images.
And one thing in there is that this light meter is reacting. It's an external light meter, so it's not something inside the camera, and it's acting exactly at the same moment of, or not the same moment, some milliseconds before the aperture is open, the shutter is opening, and the picture is taken. So this means that you really get the latest information about the ground you're looking at to read out the light and then choose the right aperture for that.
Okay, one question that came in was on burst rate, and the question was what's the fastest burst rate which you can run the camera?
With the 80 megapixel, at the moment there are two possibilities to store the data. One is on a computer, which we can supply it with a FireWire, interface. There we are a little bit limited by the FireWire, so we are around 2.8 to 3 seconds to store the images. The second possibility is to store on a compact flash card. And on compact flash card, at the moment, it's also nearly the same number, but we got the information from phase 1 that end of this month, beginning of next month, there will be a firmware release which will speed up the time to capture on compact flash card, and then we are very sure to reach 2 seconds with that. Please keep in mind that the complete readout time for the sensor itself is 1.5 seconds. So we will never get better than 1.5 seconds because that's the real time you need to read out the data from this 80 megapixel sensors and buffer it somewhere in a FIFO buffer in the camera, and then we have the storage time. The next thing is that phase 1 announced that beginning of next year there will be a USB 3 connection or interface for this camera. So at this moment it will be also possible to use USB 3, and with USB 3 we also think that we will be around 1.8 to 2 seconds, depending of course then on the computer which is storing and what's behind it.
All right, one question that came in was on comparison to large format cameras. How do medium format cameras compare to large format cameras? Maybe a generic question, but maybe we can put some light into that.
Okay, what I had before in my presentation is that medium reached today analog large format camera resolution scanned with 20 micron. Today, what we're talking about in our photogrammetric world about large format cameras, it's this what we have with the DMC2, where the high end is 250 megapixel, or the Vexel Ultracam Eagle and things like that. This is complete different kind of cameras, and to compare them, it's very difficult. First of all, they have this black and white sensors in the center. Then they have the 4 color bands, RGB plus IR. They have a different way of forward motion compensation, and. But these cameras are 80 kilogram or more. They have storage units which are different size. Then they have they need different planes. They need gyro-stabilized mounts, large gyro-stabilized mounts, and. So yes, if you go in and you have a complete survey of Germany, let's say, and you want to do it with a medium format camera, I would say you must be very, very crazy, because it will take you too much images and to compare what you can do with the so-called large format digital ones. But you need special planes, twin engine or single engine turboprop, and. So the medium format cameras are more going in the direction being either embedded with a LiDAR system, because then the opening angle of the LiDAR and the opening angle of the camera fits very well to each other, so it's a perfect match. That's the one thing. The other thing is all the smaller projects where you have villages in Europe or small cities or open minings or corridor surveys, and. Their medium format could be really a nice alternative, because you have to keep in mind the price of the camera is far less from what a large format costs you. You can put it in your ultralight or in your echo plane, so costs of operations are very low compared to twin engine turboprop, where, by the way, a second is already several euro being operational in the air, and. So I see it very clearly that it's not, you cannot compare them easily, but there's still comparison in this way, that the images are nice from both of them, but they are going in different directions from the job.
All right, thank you very much. And with that, I would look for one more question. The question was, what kind of image types is the camera producing?
Sorry, can you repeat that?
What image formats is the camera producing?
Okay. The camera itself is storing during operation raw data. This is mainly the pure information, how many photons were collected from each pixel, what was the filter in front of the pixel to make clear what color it is, and this is digitized in 16-bit. And this is a kind of raw data which is stored during the mission. Later on, you need software. It's Capture One software from Phase 1, which is coming together with the camera, or it's also free of charge download from the internet available from the software if you only operate it with digital bags. And this software allows you to develop, and this word is really used for that, the raw data into a TIFF or a JPEG. And TIFF is normally what is used in our post-processing software.
Good. With that, I would like to wrap up today's webinar. I thank everyone for joining us. If there have been any questions that we could not answer in this webinar, we will answer them via email, or you can also reach us at the given email addresses to spatial_info@trimble.com. Thanks a lot for joining us today.